Hey everyone, welcome back. Today I'd like to talk to you about a small portion of a larger project that I'm working on. And the small portion that we're going to be talking about today is data compression. Now, data compression is used for a lot of different things. It's used to compress audio, it's used to compress video, usually for the purposes of streaming. Sometimes it's used to compress files and data so that they can be stored on smaller media. And sometimes data compression is done as a method of data encryption. So today we're going to take a look at just exactly what data compression is and talk about it as it relates to encryption and ciphers. And then we're going to talk about a practical implementation of this. So let's get started. So I've got the Wikipedia website for data compression pulled up, and I want to start here because it's important to understand what data compression is, and then we're going to cover ciphers because that will become important too, and how the two relate to each other. So, according to this Wikipedia article, data compression is the process of encoding information using fewer bits than the original representation. Any particular compression is either lossy or lossless. Now, the difference between those two things here is lossless is a method of compression conceptually where the compressed data on the receiving end or the source end where it was compressed can be decompressed into the exact representation of what it was before it was compressed. There's no loss, thus the term lossless. Lossy is a form of compression usually used for things like audio or pictures or videos where you're willing to give up some of the quality of the original file in return for a better compression rate. And as a result, what you get back out of it is a facsimile of what was originally compressed. Now, that's not. It depends on the compression rate and it depends upon a number of other factors, but usually to the ear, to the eye, uh, if the compression is good, the loss is minimal enough that you wouldn't be able to tell between what was decompressed and what the original file looked like. Okay, so how does this relate to ciphers? Well, let's flip over to ciphers and get a definition there real quick. And then I'll show you a cipher, and then I'll show you how the two relate. So it says, a cipher is an algorithm for performing encryption or decryption, a series of well-defined steps that can be followed as a procedure. Now, ciphers have been around since long before computing was. In fact, I'll show you just a really basic cipher table as it stands. This is the 26 letters of the alphabet. And on the outer ring, we've got the alphabet in order. And on the inner ring, we have a shifted alphabet. And how this works is if you were to write out a plain text sentence, we'll say the word that. You would go to your outer cipher here, or your plain text, and look at the T, and you'll see that the inner cipher key has an H, so you would replace the T with an H. You would replace the A with an O, or I'm sorry, you have to go to H first. You'd replace the H with a V, you'd replace the A with an O, and then you'd replace the second T with an H. And you would have something that looked like garbage. You wouldn't be able to tell what it is, except for if you had this key and could quote unquote decrypt it. Alright, so that's the basic concept of a cipher. and we've talked about data compression. Now, how do the two of these relate to each other? Well, in order to understand that, we need to talk about a base concept in computing called binary, or base 2 math. If we have a look at counting in binary, because this is where it's going to get important, the thing to know about computers is they run on ones and zeros. I'm sure you've heard that a lot, but most people probably don't understand exactly what that means. Well, that means that a bit is represented as a 0 or a 1, an on or an off. And based on sequences of zeros and ones that are processed through the computer can do different things with that. If you look at this table over on the right, you can see we have a decimal number in base 10, and on the right hand side of this table we have a sequence of ones and zeros, and these are the representations of those decimal numbers in base 2 math. So let's quick cover that, and I'll show you exactly how that works. So we have a sequence of squares here. You'll count 8 of them. And what this represents is a byte. And what a byte is basically a predetermined and pre-agreed upon container to store information. And a byte is made up of 8 bits. So you can have 1 0, 1 0, 1 0, and we'll just go ahead and put zeros in all of these. And whatever combination of ones and zeros that you have in here represents a byte of data. Now, as that relates to base 2 math, how this works out is you have from right to left the values 1, 2, 4, 8, 16, 32, 64, and 128. Now, how do we come to those numbers? Well, that's because this is base 2 math. So the 1 position can have on or off. The 2 position, if you work it out in base 2 math, is the 1 position times 2 for base 2. Now the 2 position is 2 times 2. The 8 position is 4 times 2, and so on and so forth. So each one of these value positions here is 2 times the previous number, because this is base 2 math. And what that means is that if you work out every combination of ones and zeros you can have in a byte, that represents the decimal numbers 0 through 255, which is equal to 256 possible combinations of ones and zeros. Now, why did I cover binary math, and how does this relate to compression and ciphers? Well, let's go take a look at a table here. What we're going to take a look at is something called Ascii. And what Ascii is a predefined and agreed upon way to represent bytes as different characters. This is called an encoding method. And this was agreed upon decades ago. This has since been expanded into something called Unicode, which represents different letters and characters and symbols from all over the world. Ascii was designed as a United States standard, so this has since been expanded, and most places don't use straight up Ascii anymore. They use Unicode, but for sake of reference and ease, we're going to stick with Ascii for the moment. Now you'll see on this table that we have binary representations, we have symbols associated, and we have some other things available here. We have decimal, octal, hex, HTML number, HTML name, and a description. And the reason why we have these binary representations and then other columns showing what these are is because depending on what you're trying to do, you're using a different encoding method. So, for example, we have the $sign here, and the $sign has a binary representation of 001, 001, 00. So let's go ahead and flip back over to our table here and have a quick look at that. Okay, now if you'll recall, we're going to talk about the $sign here. I said that had a binary representation of 001, 001, 00. Now if we go back and look at that table again, we'll see that that has a decimal representation of 36 and a hex representation of 24. Let me show you how that works. So you'll remember that we had values here. We have 128, 64, 32, 16, 8, 4, 2, and 1. Now, I said that this has a decimal representation of 36. Well, how did we come up with that? Well, we see we have a 1 or an on at position 32, and we have a 1 or an on at position 4. And 32 plus 4 is 36. So that's how decimal works. Decimal is literally the math representation of this byte in a numerical format. Now I said that we had another, we've got several other, but I'm going to talk about hex because that'll be important later. We had a hexadecimal representation of 24. Now I say 24 and not 24 for a very specific reason. And that's because when you're talking about hexadecimal, hexadecimal literally splits the byte in half to represent it. And what it does is it shifts so that you have 2 half bytes of representation. So instead of 1 through 128 for positions, you have 1 through 8 on one side and 1 through 8 on the other. And so if you look at this split up byte, you'll see on the left side we have position 2 on, which represents 2, and on the right side we have position 4 on, which represents 4. Now hexadecimal, because if you add this up, can be the numbers 0 through 15. When you see it on a hexadecimal chart, is not represented in the numbers 0 through 15. It's represented as 0 through 9 and the letters A through F. So you can have all the way from 00 up to FF. And that's why when I talk about this, I don't talk about this as the value 24. I talk about this as the value 24. So, how exactly does this all relate to data compression? Well, let's switch over to an example of a data compression algorithm, and I'll show you how that works. This is called Huffman Coding. This is a compression algorithm come up with by a man named David Huffman. And how this works is you'll see this table off to the right. It's an example. And what this is you'll see that there's a text here that says, this is an example of a Huffman tree. And when you run that sentence through the Huffman compression method, what it does is it takes this entire sentence and it breaks it down, and it counts how many different characters are in the sentence and the frequency of each character. And what it does is, based on the tree that it generates from that, it breaks it down into based on the frequency, it will compress or come up with a different way to represent that particular character. So for example, we have space here, which it's changing to a code of 111. If we look at Ascii, space is represented by binary as this byte as 001 00000, or decimal of 32. So if we go back over here, you'll see that we've reduced the amount of space that the representation of space takes up from 8 bits down to 3. Now this is a great encoding and data compression method, and I definitely invite you to take a look at that in depth. This is a fun little project, and I've worked on it before, but it has its disadvantages. And you'll notice, if you continue reading the text down here, encoding the sentence with this code requires 135 or 147 as opposed to 288 or 180 bits if 36 characters of 8 or 5 bits were used. Okay, so it does provide a good amount of compression. If you work out the math on that, it's just a little over 50% compression rate. The problem with this isn't the compression, it's the fact that this is a dynamic method. For each piece of data that you put into it, it has to create a key and assign out values for each possible character. And for the sake of data that you're just storing inside a program for use later to save space and memory, that's okay to do because the program has the key internal to it and it can decompress that data later. But if you're planning to store that data out or transmit it to another machine, well, then you have to transmit the key with it or store the key. And at that point, it's A, no longer secure because the key's been provided with the data, and B, it's no longer valid as a good compression method because the key that you're having to transmit with the data takes up space of its own. So as it relates to a method of compression that you would use to store data or transmit it to another location, I don't recommend this. So let's look at a practical way where we can compress data and still have the benefits of compression and the security of a cipher. I didn't ask you to open that. Please close that. Thank you. I have to find it here. Okay. So an example of, we'll say, compression of an image file. So if you run it through the right algorithm here, what can happen is the algorithm will go and it'll look at that picture pixel by pixel, and it'll say, okay, at positions 0 through 5 we have white pixels, and then at the next pixel and the next 279 pixels after that, they're all red. And what you've done there is you've taken a representation of the data, as it were, in that picture and compressed it down into a much smaller representation, because what you're now storing isn't the exact data, it's basically a math way to recreate the image from its original source. It's instructions on how to reassemble it. And when you work it out, that's basically what all compression is a way to represent the data in a smaller format, basically by using instructions on how to recreate the data. So I'm going to switch over to, before I go to this, I'm going to talk about the type of data that I'm trying to compress, and then we're going to give you a practical example of how this can be done. So we're looking at what's called an NMEA sentence, which is something used on GPS receivers. And there are a number of different types of NMEA sentences. If we scroll back up to the top, these are all the different types of sentences you can have. In my case, I'll be using GPGGA and GPRMC. So let's go back to GPRMC and talk about that briefly. You'll notice that all of these GPS sentences have the same structured format. They have a $sign at the front, a sequence of 5 characters here that represent what type of sentence it is, and then comma-separated values followed by an asterisk at the end and a code. And that code, as I had been talking about earlier, is stored as hexadecimal. Now, I won't get into the XOR math that comes to represent that, but basically what that hexadecimal code at the end is called an XOR checksum value. And if you run it through the right math here, when you add all these characters up or run them through an XOR checksum comparison, it will come out with the value 62 at the end. So this is the type of data that I'm looking to compress and either store or transmit to another location. So if you work it out, when it comes down to it, and I've written down part of that sentence that we were just looking at, I've done the workup on this already. For the data that I'm trying to compress and store or transmit, I have the values 0 through 9, the characters $, comma, period, an asterisk, and I have the letters A through F because I have the hexadecimal code that I need to possibly have. I have G, P, R, M. I have N for north, S for south, W for west, and there's a couple of other characters smattered in there, but you get the idea. But when you come right down to it, I have 30 different character representations that I need to work with. Now, how can I compress that down? Well, if you work it out, you can do this a few different ways. If you'll remember our bit values here, 8, 16, if we stop right here at 5 bits, then you'll remember that if you work out this math, this comes up with 32 different possible values, which is definitely more than the 30 different representations I need. But the problem with this is, in order to transmit the data, the data that's being transmitted has to be transmitted in full byte format. So even if we compress this representation of $sign down into 5-bit size, it still has to be transmitted as a full 8-bit byte. What I need is a way to store more than one character representation inside the same byte value. So how do we do that? Well, as it turns out, we've actually been provided with a way in hexadecimal. You'll recall that you can split the byte in half as a representation, and you have 1, 2, 4, and 8 on both sides, or 0 through 15 as a representation. Well, that's great. That means that I've got 15 possible combinations of characters that I can represent, but, or I'm sorry, 16, but that doesn't really do me a great deal of good as it relates to trying to store 30 different values. How do we get 30 different values stored inside 2 half bytes here? Well, let's take a look at how we might do that. Let's say we're going to represent 2 different characters with the same bit value. We'll say, for example, here that we're going to store $sign and G with the same bit value, and we'll call it like 1010. Okay? So we have $sign on this side of the byte because we're going to go from left to right in storage order. So we'll have 101010 on this side, and we'll have 1010 on this side. Great, we've just compressed 2 different characters into the same byte. But there's a problem here. When we store this out, even though we've decided arbitrarily to use the same value for both these characters, when we go to decompress it, we've provided no way for the decompression sequence to know whether, when it converts this back, whether it's supposed to be a $sign or a G. Well, as I was talking about earlier in the concept of image instructions on how to reassemble an image as a compression method, we can do something very similar here. What we do is when we store out the representations or the encoding method for each of these characters, we do it in a dictionary where we say 1010 is G in this dictionary, and then we have a second dictionary that also has 1010 as a representation of $sign. And then what we do is at the end of each of those libraries, we reserve 1 byte representation. So that provides us, instead of 16 possible values, that comes up as 0 through 14, or 15 possible values. And that reserved representation at the end, which I've, in this case, done as 1111, represents an instruction to the decompression sequence. What that says is any time that you run into this sequence, you need to change which dictionary you're looking at for the next X number of characters until you run into the next reserved byte. So in my case, because all of my sentences always start with a $sign, I will always start in one library, and then any time that I need to change to the other, I'm sorry, not library, dictionary, anytime I need to change to another dictionary for the next character that's being represented, I put a reserved byte in there. So as this would look based on what we arbitrarily decided here, we'll decide another value. We decide 1010 for $ and G. We'll say we're going to represent P with 0001. Okay, so what we would do here is when we do the compression, we look at the first dictionary for the $, and we say, okay, the $, equals 1010. And then when we look at the next character, we go, well, wait a minute, that's in the other dictionary, so I'm going to tack on 1111 here as a flip, and then I'm going to proceed to start compression on the next byte. And the next byte here is a G, so we're going to say this is 1010, and then it'll look at the next byte and it'll go, alright, that's a P. I don't need to switch again. I'll just tack this on to the end, and that will be 0001. So now we've reduced the amount of space that the first 3 characters are taking up from 3 bytes down into 2. And if you do this right, the fewer number of times that you have to flip back and forth between dictionaries, the more compressed the data will be. Now, as a matter of practice, you will never get 50% or better compression rate, simply because you're going to have to change libraries. And each time that, or I'm sorry, not libraries, dictionaries. Each time that you have to change dictionaries for compression or decompression, you add more data into the original string. And so, let's see, let me flip back. Since we have 66 possible values here, but we're having to flip, we'll call it 5 times. We'll say it has to flip about 5 times, depending on how you lay out your dictionaries. You can compress that down into something like, depending on the data that you're getting out, somewhere between 35 to 38 bytes. As a representation of 66 original bytes that you had to store, that works out to something like about 40, say about 43% compression, which is, as a matter of practicality, is not bad, because what you've done here is, as long as you're using the same program on both the encoding machine and the decoding machine, you've created a way to achieve 43% compression, transmit the data, and decompress it on the other end. And you didn't have to send the key, because both programs have the predefined key. And as an added bonus, it doubles as a cipher, because unless you have the key on both sides, the information's worthless. You don't know how many original characters you had in the data, and you don't know what each representation is. Okay, so we've worked out all of this now on paper, and you're probably wondering, why is it that we went to the trouble of doing this all in this method instead of just coding this out? Well, when you do coding, it's usually a good idea, if you know what you need to do, to sort of lay that out in a human understandable logic concept, whether that be on paper or by typing it out in a document or whatever, because when you go to code that, the coding representation of your mental logic generally are 2 different things. You'll find out that in specified language that you have to approach that logic from a different direction. So now that we've worked out the logic as it relates here, let's go and take a look at the coding representation of this Okay, so we've gone ahead and switched over to the computer now. Let's take a look at the practical end of this. Now you'll remember we looked at this sentence when we were working at the logic on paper. Let's go ahead and copy that sentence. We're going to go ahead and paste that into the program. And run it. Okay. Now, this is the original sentence. Count it up, 66 bytes. Here's the compressed format of that. Compressed is 38 bytes, as I expected. It'd be right in that range. And that means that this is 57% of the original size, or as I had mentioned, it works out to about 43% compression. Now this is doing some other things here, and I'm not really going to get into some of that, but we'll go ahead and flip over into the code. And this was done in a language called Python. Now you can, since we worked out the logic on paper, the beauty of that is that this can translate into basically any language you want. As long as you understand the logic, you can recreate this. Now this is not the exact code. The code is actually in this functions module that I've written, but it takes the original string here. I'm showing you this just to prove that I'm not just trying to fool you. Prints out the original string, checks its length, and then it runs the string through the compression function. And then you'll remember, we'll go and flip back, shows you toward the end here what the original string looked like. When it prints that out, it's reassembling the string from the compressed representation that we've got back and then printing that out. So it's not printing the original string twice. It actually is decompressing it. So let's take a look at the code in question here. Let's decompress and the compression string, or the compression function. Okay, so we're looking at the compression function logic here. You'll notice we have our two dictionaries. We have matching representations of bytes for each possible character that we need to store out. And then at the end of each of those is this reserved byte. And this is actually never referenced as relates to the dictionary itself, either on the compression or the decompression. This doesn't technically need to be here, but I put it here just for my own sanity, so I don't go back and try and tack on another representation for a character and discover I can't use it. So we take the string input from the primary program, and we convert it into a list. And then we start this local value called last character, and that'll get important here in a second. We also start an integer called I at 0, so we're starting at the beginning. And then we start a while loop. Now I'm sure for those of you that have done Python, you're probably wondering why I chose to do while instead of doing a for loop, since we're working against the list here. And the reason for that is because during both the compression and the decompression cycles, the length of the list will actually change. We have to do this as while, because each time this loop is run, this gets reevaluated. Whereas if you were to do it as for, it's statically set at the start of the loop, and that's never reevaluated. And because the length of the list will change, that doesn't work out so hot. So we do this as a while. and we look at the first index position in this list, and we look to see if it's in the number ciphers values. And we discover, because it's in the number ciphers, that it is right there. Now, I've done this on purpose. All my sentences are going to start with this $sign, so I'm always starting with the same dictionary. If that's not the case in your case, what you will have to do is have two reserved values, and at the beginning of the sentence, you have to put in one of those reserved values, insert it, so that when the decompression runs, it knows which library to look at, or which dictionary, because if you don't, it'll just make the assumption that it's going to run off of one or the other, and it'll decompress it incorrectly. So we look, we say, is this in the values of the number cipher? Well, yes it is. So it goes through, and it says, let's look at all the value and key pairs in that. And it goes and it does a check first of this. Now you'll remember that we set that to -1, and that's not a value that'll match on either of these, which is fine. We want to start it at an unchecked value so we don't accidentally tack this on the front of a compression sequence by accident. So it looks at it, it says, is the last character equal to 1? Well, no, it's not. So we're going to skip that. And then we're going to flip over, and it's going to go, oh yes, this matches at that index, and we're going to replace that representation of $sign, in this case, as right here, we're going to replace it with this byte representation instead. And then we're going to break from the loop, and we're going to start over. And it's going to look at the next value, and it's going to go, all right, is that in the number ciphers values? And in this case, because the next one's a G, it's going to go, well, no. And you forgot to mention here, I'm sorry, after it replaces the value with the key, it sets last character to 0, and it does that so it knows that the last dictionary that we used was the number cipher. It breaks out, it comes through here again. Does it match? No, it doesn't, so we're going to jump down to here. And yes, it does match the character cipher values. And so it's going to go through and it's going to read through the whole dictionary again for the character ciphers. And it's going to go, oh yeah, that actually did happen. The last one was in the other dictionary, so we need to insert a byte here between the $sign and the G, which would be right here. Yep. Okay, and then it's going to break out of that. Now, because we inserted this byte value, when it goes to increment this and goes to the next index character, it's going to run into this G again, because we inserted this between the $ and the G. So at this point we have a byte replacement representation of the $sign. We have a dictionary change byte inserted, and now we're back at G, and now it's going to come through here again, and it's going to say, well, the last character wasn't 0, so we're going to skip down to here because we changed it to 1 when it inserted this. And we're going to go through, and now we're going to replace the G with the key representation of it. And we're going to go through and do this for each character that it runs into the string until it gets all the way to the end. Now, what we have is we still have 66 total bytes. We just have key representations of each of those bytes replacing the characters. Now we need to compress that data. So how do we do that? Well, because this byte leads with 4 zeros, we can do this fun little binary math trick called bit shifting. What we do is we'll reset our counter to 0, and we're going to open up a new list here for the actual compressed data. We're going to run this while loop again for the same reason. And we're going to start with index position 0. Now index position 0 in this case is different than all the other index positions because when you declare an empty list, you can't append to it. There's nothing inside it. You have to insert something first at, in this case, position 0, so that it has something in it, and then you can append after it. So what we're doing is we're saying at this position, at index 0, we're going to take the first byte from our other list, and we're going to put it in at index position 0, and then we're going to shift the bits 4 bits to the left. So that, let's see, $, that 0001010 is now going to become 10100000. And then after that, we got this pipe on here. And what that's telling is we're still going to work with the same byte, and we're going to tack the 4-bit value for the next thing, which in this case is a dictionary change, onto the end of it. And if you remember what we were writing out on paper, this is the exact representation of that. It's putting in the 4-bit representation for $, and then the library change. And then it's cycling back through, and you'll notice I'm doing I plus equals 2 because we have to move 2 index positions. If we only move 1 and then repeat the cycle, then the next time it does a compression, it's going to make the next byte the library change, and then the byte after that, the G, which isn't going to work out. We're now duplicating data. So we increment by 2, we shift back through. It's not index position 0 anymore. We're now at index position 2. And now it does 2 different checks. And this wasn't something I caught initially, because most NMEA sentences will work out to an even number of characters, but there are certain instances where it'll come out odd. And you need to have a way to catch that, because what will happen here is it'll get toward the end, it'll get to the end of the list, and it'll try to tack on a byte of data that doesn't exist anymore, because this will be the last index position possible. So we put a catch in here and we say we're going to check for the length of this list -1. I won't get into that. If you don't do programming, that won't make much sense, but basically it's looking to make sure that we're not going to overflow the number of positions available in the list. And as long as we don't, it'll do this. Otherwise, it assumes that we've hit the end of the list and that we're going to overflow. And so what it does for that last byte, in instances where we have an odd number of bytes to compress, it tacks a dictionary change onto the end. And the reason why we do that rather than tacking on anything else is because when this is decompressed, that will just get stripped off and ignored. If you add anything else onto the end of it, it's going to convert it into a character that you don't want. It'll be adding data that didn't originally exist. So now we've gone through, we've compressed the string, and now we return that list to the program. Great. We've done the compression. Now let's go through the decompression. We have the same 2 dictionaries listed so that we have the associated keys to decompress. Start our counter at 0. We took the array in, the compressed data array, and now we're going to start another empty list called decompressed. We're going to start our counter at 0, look at the length, and we're going to take a byte in. Now you'll remember that this is 2 representations in the same byte. How do we get this back out and split off? Well, we're going to play some of that same bit shifting fun that we were playing with the compression sequence, and we're going to shift that first byte 4 to the left again. And now what we've done is, because we've shifted that whole byte 4 index positions to the left for bits, it's now created a 2-byte representation. Let's look at the chart down here. So here's the original that we took in. Now here's where we bit shifted it left. And this is what it looks like now at this point. Okay, now we proceed down to the next line. We have 2 more temporary variables that we work with here, and we convert this into 2 bytes because we need to split it off. And what that does is it puts B into here. This is now B. We got the pipe here, and this is now C. So we've got our 2 separate bytes, but wait, we've got a problem here because this has got way more than it needs. This is not the right representation to match the key up here. So now we take C and we bit shift it, this data, back to the right by 4 positions. And after that happens, this is what our 2 separated bytes B and C look like. Now, as I mentioned before, you can't append to an empty list, so we first insert for index position 0, and we put B into position 0, and then we append C. And we go through and we do this for each possible byte, so that we've now split the 2 character values in each byte off into their own separate bytes. We go through until we run out of them, and then we come down here and we start the actual conversion process. So we start this sort of like we had the other one up here, last character. We start this in a similar fashion, but for a different reason. Start our I back off at 0. We start our loop here. And it's going to go through, and the first thing it's going to look at in each loop is to find out if the decompressed byte that we're looking at is equal to a decimal value of 15. And you'll recall that those are our flip characters, so that we know to change dictionaries. Now in this case it'll never start with that, so this will get ignored on that first run. But if it were, what it'll do is invert the value of flip from -1 to 1. And then it goes through and it will delete that byte from the list because we don't need it anymore. And then what it does is, for instances where we tacked this onto the end of the string for odd numbers, it just breaks off because the last byte was a dictionary shift and we don't need to keep running. Now in this case, this is going to get ignored here. We're going to start with -1 to tell it that we're looking at the number ciphers, and it's going to go through and look at that entire dictionary again, and it's going to find the key that's related to the byte in the index position that we're looking at, and it's going to replace it with the equivalent value. It's going to increment I, and then we're going to break and start over, and it's going to go through and replace each one of those bytes with the equivalent character representation until all of the dictionary changes and all of the bytes are decompressed. And then we're going to start this empty string down here, and now that we've replaced all of those bytes with their character values, we're going to go through in a for loop and say to reassemble it onto a string, and then return the string to the program. Now this is how I've chosen to do this. This logic would have to be tweaked a little bit to do it another way if you have sort of random data where you're not sure how you're going to, if the character at the front end isn't always going to be in the same dictionary, you'd have to work out that logic a little bit differently. But for all intents and purposes, this could be expandable. There's a number of different ways that you could do this. You could stick with the 4-bit representation to come up with different dictionaries. And the thing to note about that is every time that you tack on a dictionary, you have to reserve a value at the end of it to represent the dictionary change, so that when it changes, it knows which dictionary to look at. So this would work out well for something like a random string where you don't know which library, or I'm sorry, which dictionary that the character representation is going to be in. You reserve a byte for each one of these dictionaries so that you can tell it when it compresses to put on a reserved byte on the front, so that when it decompresses on the other end, it knows which dictionary to look at to get the character representation out. So in this case, I've got 6 defined here, and because that means I have to reserve off that many bytes for each one of these dictionary changes, I lose 6 possible combinations, which means for each cipher dictionary I can get 10 values out of. So just be aware of that if you're to do this in this format and continue with the 4-bit representation for each character, then for each time you tack on an additional dictionary, you lose a possible byte out of all the previous ones to a reserved byte for a dictionary change. So if I were to tack on an extra one here, like cipher, then I can get 9 out of each dictionary. So it's diminishing returns. Play with it as you like. There are other ways that you can do this with the same bit shifting. For example, you could go to, say, 6 bits, in which case you get far more character representations in a library, but you can't compress it quite as far. So there aren't as many dictionary shifts because you get more in each dictionary, but you also can't compress it down. If you do 6 bits as opposed to 4, then you can compress down, let's see, 8 bits in a byte, compress down to 6. So the next equivalent representation is 24. So you can put 4 bytes down into 3. So it's not as good of a compression method, but as a cipher itself, it works out really well. In any case, this was something I thought was excellent to share. It should work out well into the larger project that I'm working on, but I wanted to share that with everybody, and I'm hoping that maybe everybody learned something today. So if you did, feel free to like and comment, maybe subscribe. I do release videos intermittently. Otherwise, have a good day, and I'll see everybody next time. Thanks.